Okay, for the reduction of order method, usually we always use this technique with the second order differential equation, which has the variable as the coefficients of the differential terms of y. With this method, we divide it into two cases again. Okay. The first case, we don't have the dependent variable y. If you take a look at your differential equation, it shouldn't have y. So I would say that fx is a function of x, the first derivative of y and the second derivative of y. See, no y. And set it equal to 0. If you have your second order differential equation in this form, then the way to find the solution is just assume p is equal to dy by dx. So the second derivative of y would be equal to the first derivative of p. See? So that means you reduce it into the first derivative. For example, if we have x times the second derivative of y minus the first derivative of y equal to 4 times x to the power 5. This differential equation, can you use the previous method to find the solution? I mean, is this equation the homogeneous or non-homogeneous differential equation? Non-homogeneous differential equation. So you would say that you would have two solutions, which is yc and yp. Can we find yc by using the previous method? Can we? If we want to find yc, we set this equation equal to 0 and write out the characteristic equation. Can you find yc by using that method? The method that we used to learn before. You have variables here, so you can. So this is only one way out for you now. Okay, now you see the point why we have to use the reduction of order instead of using the previous technique to find the solution. Okay. Then we will consider this differential equation, whether it is matching with the first case. Okay, we have x, okay, x there. We have the first derivative and second derivative, yep, we have there. And it said that we shouldn't have y, and we didn't have y. So that means it is fitting with case 1. So to find the solution of this one by the reduction of order, you got to assume p is equal to dy by dx. So in this differential equation, you have second derivative of y. So since we assume this, so the second derivative of y is equal to the first derivative of p, right? dp by dx. We plug our assumption to our differential equation. It's turning to be the first order differential equation. We rearrange the equation. Can you tell me if we want to find the solution by using the first order differential equation, what kind of technique we are going to use? This equation is a form of linear differential equation. So we are going to find the integrating factor. Our integrating factor is equal to exponential of the integral terms of px dx, and now our px is equal to minus 1 over x. Just plug in there. So from that, we would know that our integrating factor is equal to 1 over x. So We know that it's equal to 1 over x, right? We know that from our first order differential equation method, we know that our p is equal to 1 over integrating factor times integral of integrating factor times q dx plus c. Now, our integrating factor is equal to 1 over x. 1 over x is equal to x. 1 over x. Our qx is equal to 4x to the power 4. Equal to what? X to the power 4. I would put it as a C1 because we know that we have to integral more. It's not done yet, right? And we know that P is equal to dy by dx, right? Which is equal to x to the power 5 plus x c1. Can we find 1 now? Oh, can we find y now? Yes. We just move dx to the same side as x. And we do integral of both sides. So we would get y is equal to x to the power 6 divided by 6 plus if you want to know what is yc, yc is these two terms. Which one is yp? Here is yp.